Well, it is 2 p.m. and we've got a lot to cover, so I think we will get the show on the road here. Of course, I'll start just by saying welcome everyone and thank you for joining. My name is Matt Del Bono and I'm an extension support specialist with the GLASE Consortium. And today we have the pleasure of hearing from Dr. Michael Eaton, who will be presenting a webinar titled Integrating Geothermal Heating into Greenhouse Crop Production. So before we get started, I do want to very briefly introduce you to GLASE. So just quickly, we are the Greenhouse Lighting and Systems Engineering Consortium out of Cornell University, and we're here to transform greenhouse lighting and systems management to support climate smart CEA. And we do so in a number of ways, but the focus is conducting research and educating growers so that hopefully emerging technologies can be adopted faster and save growers money and ultimately reduce the environmental impact of energy use in greenhouses. So we have some key areas where we support the CEA industry and our GLASE members. And so, as I mentioned, our research is focused on greenhouses, but also includes indoor agriculture, and we seek to facilitate technology transfer. We also provide webinars, technical articles, short courses, and other workforce development initiatives to help educate growers. And finally, our membership values our networking benefits via our industry advisory board meetings, as well as the annual GLASE Summit. I do want to note that this year, the GLASE Summit will co-locate with the CE Ag World Conference and Expo in Durham, North Carolina this November. So if you are interested in participating in the program or sponsorship opportunities, please reach out to our team. I also want to briefly mention a new resource, which is the GLASE Library. The GLASE Library is a central place where you can access past webinars and other resources. And so we also have our previous short courses available there for purchase for non-GLASE members. And so we encourage you to check that out. We're also very excited to announce the launch of CEA Works, which is a training program sponsored by the U.S. Department of Agriculture's National Institute of Food and Agriculture. And so CEA Works includes 4 on-demand online courses, including Root Zone Management, CEA Business Planning 101, an overview of crop production in CEA, as well as plant physiology of CEA crops. And so those courses are actually available for purchase now, and you can begin accessing content on June 1st. And so our members are very valued, and we hope that you are potentially interested in joining GLASE. And if you would like to learn more, you can contact our team for additional information on member benefits as well as member categories to suit your needs. And lastly, I want to highlight our membership initiative called Vivid Canopy, where folks working in the CEA industry can connect and organizations can showcase how they're leading by example and hiring a more diverse workforce. So we hope that you will join our LinkedIn group to get connected. And so with all that being said, we'll shift gears here, and I want to take a moment to introduce you to our speakers. So Dr. Michael Eaton is a mechanical engineer and energy modeling specialist who holds a BS and MS in mechanical engineering from the University of Massachusetts. Michael has worked as an energy engineer where he's provided analysis for energy efficiency projects in the commercial and industrial sectors. And Michael's also earned his PhD from Cornell University and is currently a research scientist at Meta. So with all that being said, I'm going to hand things over to Michael to get us started. And while he's queuing up his presentation, I'll also just remind folks that we will have time for a Q&A at the end of this session. So we really encourage you to submit questions as we go in the Zoom Q&A, and we'll be sure to get to those at the end of Michael's presentation. And so whenever you're ready.
Thanks, Matt. Also, bad news. It wants me to quit and reopen Zoom to share. So I guess the share permission was not.
Okay. Let me see if I can.
I'll join.
Hey, hang on just a second. I'll make you a co-host, and then I think that will give you permission.
Oh, actually, yeah, that worked. Thank you. Okay. So I will share. And what is this? Okay, share.
I do see your screen. It's not
okay. That's great.
There we go. Yep.
All right. Hello, everyone. I'm Michael Eaton, and yeah, like Matt said, thank you for the introduction, Matt. I will be talking about a topic I covered as a part of my PhD dissertation research at Cornell in systems engineering. And the title is Adopting Deep Geothermal Energy for Sustainable Crop Production in Cold Climate Greenhouses. I'll go through some motivation and background, research aims, the approach, methods, results, and come back for questions. All right, so I just wanted to throw this sustainability in CEA framework up. So one way to think about it is in terms of resource use effectiveness. So how well are your inputs like energy, water, and nutrients translating into the desired outcome? So they go through some production process and you get yield and crop quality and flavor and taste. So today we're going to be talking about mostly the energy inputs because there is an energy problem in CEA. So heating costs alone can account for more of a commercial greenhouse's annual energy expenses, especially in cold climates. And this is the heating demand is highly location dependent. So a greenhouse in Phoenix is going to have a much lower kind of energy demand than a greenhouse in colder climate like Minneapolis or Helena. So this plot just shows the estimated energy consumption on a per unit area basis, so per square meter, how much energy is being demanded to maintain the conditions but there is an opportunity. So with high heat demand, there's an opportunity for geothermal energy. So geothermal energy offers a reliable and renewable solution to CEA's heating challenge. This map here shows the surface heat flux across the US. You can see that out west, there's a lot more geothermal resource. And in many cases, the geothermal energy is being extracted to produce electricity, and that's if you have very high temperatures and a very high grade resource. But out towards the east, there's only select pockets with higher heat fluxes, and we have to make do with lower temperature gradients. So geothermal resources are obviously highly location dependent as well. And New York State doesn't have a high grade geothermal resource, but there are select pockets with higher geothermal gradients, maybe favorable subsurface conditions like permeability to water flow. And the high cost of drilling is a barrier to adoption for this technology, especially in regions with lower temperatures or lower temperature gradients. So instead of producing electricity, you could use the heat directly. So direct utilization of geothermal energy has been expanding. So this plot is from a survey of direct utilization geothermal heating in 5-year increments from 1995 to 2020. And yeah, it's rapidly growing. And one of the use cases mentioned here is greenhouse heating. That's number 4. So maybe it's not as big as geothermal heat pumps for houses or something else, but it is definitely growing kind of area of interest, especially in low grade regions. You want to just use that heat directly. It's not economic to produce electricity or high temperature enough. All right, so I'll just talk a little bit about the research aims and the framework that I use to approach some questions about integrating geothermal energy into greenhouse agriculture. So the aims here are to characterize the potential for this, for integrating geothermal heating into crop production, especially in low-grade geothermal regions. The approach and the objectives here are to develop a techno-economic analysis framework to evaluate the geothermal integration into greenhouses. So is it technically possible? Is it economically favorable? And is there environmental benefit? So I'm going to present a case study of New York State estimating the emission savings and the economic performance. Want to evaluate the effects of investment credits, because I think one of the barriers is the high capital cost, the investment cost, but over time, the marginal cost or the unit cost of energy is lower. So applying an investment tax credit can really have an effect on the economics of the project. And I also want to quantify the benefits of potentially repurposing abandoned hydrocarbon wells for geothermal heating, just kind of exploratory. So the summary of this analysis is that we're looking at greenhouses, growing lettuce. It could be applied to other greenhouses, but the set points in everything modeled in the greenhouse is considering lettuce as the crop. The performance metrics we're going to use to evaluate the system are the heating system cost and the lifetime emissions associated with the heating system. And we're going to look at two different geothermal configurations. So a deep direct use heating system, and I'll explain what that is in the next few slides, and a deep closed loop system with a heat pump. And we'll look at different economic conditions. So just, no incentive, 30% tax credit, and, what if we could save on some of the drilling costs by retrofitting abandoned hydrocarbon wells. And we'll be looking at New York State counties. All right, and there's a good number of slides in the approach and method section, just detailing a lot of the inputs to this whole analysis framework. So this starts by integrating a lot of different data sets. So there's climate data from all the different locations, like the solar radiation, the temperature, wind. There's borehole measurements. So there's measurements of the subsurface conditions available in some locations in New York. And there's also locations of abandoned wells. So wells that have been plugged and are no longer economically viable for hydrocarbon production, gas or oil. So we can integrate these data sources and plug them into our models. So the models have three main components. We have a greenhouse energy model, a geothermal reservoir model, and then an economic model, so a discounted cash flow analysis. And these make up the whole analysis I'm going to present today. So just in terms of data integration, so we have the weather data, and I'm just showing a heat map here, just showing regional favorability for greenhouse, a geothermal greenhouse, just by plotting a few key variables. So the average outdoor temperature that is obviously important for the weather or for the heating demand, but as well as the surface temperature. On the bottom left plot, this shows the geothermal gradient. So the central south has kind of the highest geothermal gradients in the state. I mean, it's low for the country, but high for the state. The northeast region has the highest heating load. It's much colder up there. And the southeast towards New York City, Long Island, has more plentiful sunlight. Okay, so for the data available for the well measurements, we have some publicly available data sets from oil and gas and mining industries. So we can get subsurface temperature, the thermal properties of the subsurface, like conductivity and the heat flux, as well as the depth at these different measurements to kind of estimate what the subsurface looks like. And that will help us develop models for how the subsurface or the geothermal installation will perform. There's also a number of these wells that have been plugged and abandoned. So if we can find certain wells that are quite deep, they'll have higher temperatures, and they may be good candidates for potentially reusing them for another purpose, giving them another life. So I said I would explain the two different geothermal system models. So deep direct use is an open loop system, which means you inject cold water down into the subsurface, where it will pass through a permeable fracture network of hot rock or warmer rock. It will pick up the thermal energy by coming in contact with the rock, and then it will be pumped back up to the top where it's used for heating. The other type of system is a deep closed loop system. So unlike the deep direct use, this is closed, meaning the water is not leaving the pipes. It's not traveling through a subsurface fracture network. It's staying in this coaxial borehole heat exchanger. where water is injected into the outer annulus and produced back up through the central pipe. And as you can imagine, this has a lot lower heat transfer surface area, so the outlet temperatures are lower. We're able to extract less heat, but it's more consistent in terms of we know what the heat transfer looks like through a pipe wall, where the reservoir may have some uncertainty with the thermal properties and the hydraulic properties such as permeability. Okay, so for the greenhouse energy model, we need to know a few things. So the geometry of the greenhouse and the material definition, all the weather data input, so where is the greenhouse located, the set points and schedules of the equipment, like the lighting, the shades, etc., and the heating and cooling system specifications. So the efficiency and when the fans are on and off, when the shades are drawn, etc. And so for the greenhouse energy model, the inputs are the weather data. So we're using the typical meteorological year data set, which takes typical weather conditions for a given region and aggregates them so that we can use it for modeling the conditions of the greenhouse. So we're modeling a nominal greenhouse size. So we're modeling a greenhouse of 1 acre, and then we're kind of scaling up the heat demand to look at different greenhouse sizes. The temperature set points are 23 degrees Celsius during the daytime and 19 degrees at night. And the hot water heating system, the minimum supply temperature we're targeting is 60 degrees Celsius. So this kind of determines how deep we have to go in the subsurface to get this temperature water. So for the greenhouse options, we have a baseline greenhouse, which we kind of model with typical greenhouse parameters. So non kind of energy efficient options. And then they say that energy efficiency is the first fuel. So you can really actually reduce your load if you reduce the outside air infiltration rate, you use a thermal curtain, and there's a lower heat transfer coefficient for the material chosen. So this can help bring the economics in line for the assessment we want to make, because the capacity of the geothermal system is one of the driving factors for the cost. So if we can lower the heat demand, we can lower the cost for the heating system. And we're going to use a couple of performance metrics. So the levelized cost of heat is just the time averaged cost for every unit of heat you're using in dollars. And for the environmental performance metric, we're just going to look at the lifetime carbon emission savings compared to what? Compared to a baseline natural gas system. So we're taking how much carbon emissions would this proposed system use and compare that to the natural gas baseline system. So for the baseline system, we'll use a natural gas boiler with 90% efficiency. Capacity costs around $215 per kilowatt thermal. We have some maintenance costs, and then a natural gas marginal cost, which is typical for New York, $9.74 per million BTU, with a certain equipment lifetime. The geothermal system is a well doublet, which means there's a single injection well and a single production well. And the well completion costs are calculated via a correlation that was published in 2014, but then updated for more recent costs. The lifetime is 30 years, and we have to consider the cost of electricity for the pumping power, so pumping water into the subsurface. We're considering electric costs around 7.7 cents per kilowatt hour. So I mentioned heating capacity before, so I just wanted to show an example using Cornell greenhouse is about sizing the heating system. So if we have, this is real data from the Cornell Guterman greenhouse section for 2016. And the top plot shows the heat demand taken from the steam flow data, and the bottom plot shows the outdoor air temperature. And you can see that the peak demand is actually much higher than what's happening for the rest of the year. So when we're sizing the system, we have to size it based on the coldest night of the year, or at least you have to consider the 99th percentile of what you expect to experience, because the heat demand must be met even during these conditions. But investment costs increase by increasing the heating capacity. So we could think about potentially a hybrid system where you don't invest in a geothermal system to meet the full heating demand that's needed, because then you'll have a kind of low utilization of all that capacity. And geothermal is already a sort of expensive technology. It's already a bigger investment. So maybe there's a sweet spot for how much capacity you can design for in order to get more economic benefit. So just looking at a heat load through the year, this is hourly heat load. And the top red lines there are the full heating load for this greenhouse. But if you wanted to size a system such that you could cover 98% of the total annual energy consumed, you could actually reduce the capacity quite a bit to that blue band there. And if you wanted to size the system to cover 95% of the annual load, you could reduce the capacity to that green band there. So this would require a supplemental, maybe natural gas peaking heating unit to help get through the coldest nights of the year, but you'll get a much higher utilization of the geothermal system, which makes the economics a lot more favorable. So for the rest of the analysis, I'm just going to show what the 95% sizing strategy would yield in New York. This slide is a bit technical, but we modeled the subsurface temperature just using that geothermal data that I mentioned before. All those measurements in New York, we can get an idea of what the temperature gradient is. So how fast does the temperature rise the deeper you go? And then we can use this to model the production temperature over time. And we said we wanted to meet a minimum production temperature. And we also have a requirement that as the reservoir, the subsurface reservoir, cools down, we don't want it to cool down more than 20% in 30 years. So we have to limit our pumping rate to maintain kind of a sustainable investment. So yeah, this plot shows the heat production over 30 years from a example reservoir. So the top plot just shows that it's slightly declining due to the temperature drawdown of the reservoir. So we're limiting to about 20% drawdown in 30 years for all the reservoirs we're going to size here today. So for the deep closed loop model, we have the cross-section geometry here, and it's a conduction dominated heat transfer. So it's very less surface area and it's conduction dominated, so it's a bit lower production. We have some inputs to model the economics of the investment here and assumed efficiency about the coefficient of performance for how this system would work. Okay, so I think the results and findings might be more illustrative of what we're trying to find, because there's a lot of parameters involved in the models, but I think the results and the findings can help translate that into the cost and the benefit. So this plot here, just to orient you, the vertical axis is the depth of a geothermal reservoir. So if you're targeting a reservoir at 2,500 meters depth, you could support a greenhouse of somewhere between 8 and 11 acres size. And if you go deeper, you can support more greenhouse area. And this kind of helps to scale or leverage the economy of scale of having larger greenhouses, more heat demand, and also higher temperatures. And additionally, if you can lower the injection temperature, you can also increase the supportable greenhouse size. So this looks at 3 different injection temperatures for the depth profile. So 30 degrees C up to 40 degrees C. And it does make a difference in terms of how much heat you can extract from the subsurface if you have lower injection temperature. How does this translate economically? So as you go down, you drill deeper, you get lower and lower unit cost of heating. So we want this number to be as low as possible. So ideally, we would drill it as deeply as we can, targeting a reservoir that has favorable permeability. So for higher injection temperatures, there's kind of a steeper benefit the deeper you go. So all the way over to the right, the red triangles show that as you drill deeper, you're getting a lot better economies of scale for your drilling costs. So this is the general trend for different regions. And now in general, as deep, the deeper you go, these are the trends in terms of the economics. And then I want to map that onto the state of New York to just show the range of different counties in New York. So the geothermal levelized cost of heating ranges between $11 and $21 here, and natural gas with the unit price of $9.70 and the investment costs over its lifetime is around $12.40 per million BTUs. And I just want to focus down here on Tompkins County, and you can see it's reaching around $12 per million BTU. And the south central counties, Chemung, Tioga, Tompkins are the most competitive because they had the highest geothermal gradient, and they also have reasonable heating loads. It's not super high heating loads. So those were the most competitive in terms of location, regions in the state. And with the tax credit, if there was a 30% investment tax credit, the lifetime unit cost is very competitive with natural gas. Tompkins dropping from $12 to $9 per million BTU. And this was all for the deep direct utilization geothermal system. And now I'm going to get into the deep closed loop system. So the deep closed loop system, it peaks early. So you start injecting water and you're producing high temperatures for a very short period of time, but then after that, it holds a steady value for years. So it's consistent in terms of how much heat you're going to produce over the lifetime of the system, but we just wish that heat was a little bit higher. And it turns out that the amount of heat that you can produce over the lifetime, that steady state value, shown on the plot on the left, really depends on the flow rate and the injection temperature. So I explored a few different flow rates and injection temperatures and what the performance would be in different areas of the state, so places that have different thermal gradients. And it produces kind of a big heat map. The green is generally better and the red is generally worse for this. So let me orient you to this table here. So on the vertical axis, you have the mass flow rate. So at the top, you have low flow. At the bottom, you have higher flow. And on the going left to right, you're increasing your injection temperature. So in general, you're getting more heat production if you inject with low temperatures and you have water really ripping through the system. But there's usually a trade-off. So if you can increase the heat production, you're also lowering your production temperature. So the fluid that comes out of this heat exchanger is actually cooler, which is not good because we have to use a heat pump to increase that temperature to a temperature that could be used for heating. So it has to be higher than whatever the set point is on the outlet of the heat pump. So this is just the extracted temperature. Using the heat pump, you can bump that temperature up such that you'll be providing hot air to the greenhouse. So there's kind of a trade-off with heat production and production temperature there, as well as the efficiency. So if you look at the system COP or the coefficient of performance, so how much power does it cost you to get a certain amount of heat? That's what the COP is. So if you have very high flow rates, the COP becomes much worse because you have more frictional losses, much more pumping energy required. The flow rates between or below 16 kilograms per second, you can get a coefficient of performance above 5, which is very good for heat pump. And now in terms of annual emissions, there's kind of a sweet spot. So the highest emission savings are not at the highest heat production or the highest outlet temperature, but they're somewhere in the middle. So the mass flow rate is somewhere between 10 and 16 kilograms per second, and having lower injection temperatures gets you the highest emission savings in terms of tons per year of CO2 saved. So this is great. However, the system, like I said, the deep closed loop system is able to produce a lot or generate a lot lower amounts of heat than the open loop system. So you can support greenhouses somewhere between 6 and 8 acres. But assuming we can retrofit some of these abandoned hydrocarbon wells, you can get very desirable unit cost for heating. So somewhere around $5.50 per million BTUs. And this is using the actual gradients for actual abandoned wells in these different counties. So you can get very good prices, but for a very small greenhouse. If you can find a cluster of these abandoned wells, you can scale it up a bit. But it is, these economics are all kind of based on using, avoiding some of the drilling costs for installing these systems. All right, and so if we look at kind of the annual avoided CO2 emissions on a per unit lettuce basis, so both geothermal systems save around 90% of the carbon emissions compared to the natural gas heating system. So these are emissions associated with the heating system only. And if you have a less efficient greenhouse to start with, your savings are higher. But if you have an efficient greenhouse to start with, your emission savings are somewhere between 0.7 to 1.2 kilograms of CO2 per kilogram of lettuce, depending on the location. And just as a reference point, field lettuce coming from California being delivered to New York customers, the CO2 per, the kilograms of CO2 per kilogram of lettuce produced was around 1.2, just as a kind of anchor point for understanding these numbers. And now I want to just go over some key takeaways and conclusions from this presentation. So carbon emissions can be reduced significantly with geothermal systems. So with the deep direct use system, 94% emission savings were achieved. And with the deep closed loop system, because it's using a heat pump, which requires a bit more electricity, 86% of the carbon emissions were reduced. But with favorable conditions, the deep direct use system can be competitive with natural gas baseline, even on its own, so without tax incentives, depending on the location. But after there is a 30% tax credit applied, it becomes much more competitive. So the best locations achieve somewhere around $9 per million BTUs compared to around $12 or $12.40 for natural gas. And yeah, if repurposing hydrocarbon wells can reduce the levelized cost of heat by around 42%, and the best locations could achieve levelized costs of around $7 per million BTUs for the deep direct use heating system, and $5.50, or what does that say, $5.10 for per MMBTU for the deep closed system. And these are some references that I was using, but I want to welcome any questions. I realized I kind of zipped through that presentation. So if there's questions, please feel free to ask. I want to make sure everyone is satisfied. Thanks.